Welcome to our next lesson in our block on pneumatics. In our last lesson, we looked at how we can mechanically compress air and how does that occur and how can we use this compressed air in various ways. As we recall from that lesson, an air compressor works by creating a vacuum, sucking air into a cylinder by a piston, and then using that piston to force this newly compressed air through a second valve and into a storage tank. Once the compressed air is in a storage place, it can then be released through a series of valves and can be used to power tools or various other things. So by looking at the way that we compress air, we can get an understanding of how compressed air can be used in a variety of ways. Today, we're going to be looking at how air pressure affects sound. Now, one of the tools that we looked at with our compressed air was an air sprayer. Our air sprayer is a very, very simple mechanism in which this compressed air in a tube goes in through a valve that is controlled by a lever, and when the lever is pulled down and the valve is opened, the air from its compressed state moves out through a hole. Now, the hole of an air sprayer is very small, and the way that the air sprayer is able to work is that this highly compressed air is forced into a smaller and smaller passageway until it escapes through a tiny hole. When it escapes through this hole, that has increased the amount of pressure that the air escapes by. And so, by releasing this compressed air through a small space, we increase the amount of pressure. Well, in so doing, we create quite often a sound. We can hear this air escaping through the air sprayer with a hissing sound of air being sprayed. Well, it's very similar to the idea that if we had compressed air filling an automobile tire, and we managed to put a very small hole in this tire, then we're also going to hear the hissing of escaped air. So when we think about the idea of sound being produced by air, we should be thinking about vibration. When vibrations are made by air escaping through a small place, it makes a vibration, travels through the air, and then we receive that vibration inside our ears. It triggers the bones in our ears, and we're able to hear the sound of the vibration of air escaping. Well, this is important because for us to understand how air pressure affects sound, we have to realize that air traveling through a concentrated passage is going to be able to create vibrations. Now, one of the easiest ways for us to do this is to take our air from our lungs, which is compressed, and then to release it through our mouths. But instead of just breathing it out, we can do blowing, which creates a bit of a sound, but we also can alter the way that that air escapes through our mouth. If we use our tongue and lips in the right way, then we can effectively bend the air passage so it has to go up over our tongue and then out through the lips. In doing so, we're able to create an entirely different sound. A whistling sound, of course, is made by changing the way that pressured air flows through a space. So, how does this affect sound and music? Well, we know that by taking airflow and moving it through a space and then controlling the way that that air vibrates, we can create a variety of different sounds. And so, one of the tools that we have for creating sound with compressed air is, of course, the favorite Waldorf recorder. Now, Waldorf, or a recorder, we use them in our Waldorf schools. A recorder is a device that is using compressed air from our breath, but taking that air and forcing it through a very specific type of a channel. When we look at our recorder, we see that when we deliver the air, we're breathing it through a slot in the mouthpiece. Now, by creating this fairly narrow and flat slot, we're controlling the way in which the air passes through. we then see that where the slot exits, it opens up into an opening in the actual recorder mouthpiece. Now, if we look carefully at the opening, we see that there is a slope, or almost a blade-like action that is happening right here where the air will escape. And of course, we see that there is a hole in order to allow the air to escape through that. What is happening here is that as the air passes through this original part of the mouthpiece, it hits that slanted space, and a certain amount of the air is going to exit right out through that slanted space. But when that air is exiting out through the hole, another portion of the air is being split and forced down into the tube of the recorder itself. And so by doing this, what we've done is created a fluctuating vacuum pattern. Some of the air exits, which creates a vacuum inside the tube, which causes other air to get pulled down into the tube, which pressurizes the tube. But when it becomes pressurized, then some of the other air escapes back out the top, and we have a fluctuating pattern of air being brought in and out of the tube. That fluctuation is going to cause a wavelength of the air as it vibrates through the tube. Well, it's this vibration that is causing the sound that is produced by an instrument. So the top of a recorder by itself is essentially like a whistle. The air escaping is going to fluctuate in and out, and it's going to move out of the hole as well as the hole near the mouthpiece. And of course, we get a very high pitch because that vibration is not traveling very far. Now, how we control an instrument is by determining how long the wavelengths will be of our vibrations. So if we are using vibrating air, we're going to determine by the holes on the recorder how long the wavelength of air will be. In a shorter wavelength, we're going to have a higher pitch. And the reason is that a shorter wavelength has a higher frequency. And the word frequency means how much distance between the peak to peak of a wave or from the trough to trough of a wave, both of which are the same measurement. If that is a shorter distance, then we're going to have a higher frequency. And if it is a longer wavelength, we will have a lower frequency, meaning more distance between each wave. And a lower frequency is going to give us a lower pitch. And so we control the sound by the number of holes that we cover up. Every time we cover a hole on the recorder, we make the sound waves travel further. So if we only cover a couple of holes near the top, we are able to get a higher pitch. If we cover more holes, thereby lengthening the vibration that is escaping through the cylinder, we've now lowered the pitch. And if we cover all of the holes on the recorder, now the air is escaping through the end of the recorder and we'll have the lowest frequency and the lowest pitch. So, if we take that premise and we take it to another step, we can look at another one of the most amazing instruments that have been created by people. It is the pipe organ. And the pipe organ is a wonderful example about how air pressure can affect sound. Pipe organs are generally in large churches around the world and have been around for centuries and centuries. People figured out this technology a long, long time ago. Let's look at how a pipe organ actually works. A pipe organ actually does have an air compression storage chamber. In old pipe organs, they have a large box, essentially, that is airtight. But on the top of the box, there is some form of bellows. Now, a bellows is an object for pressurizing air. It's a very, very old thing. In the old bellows, one would have two handles, a sort of leathery, flexible thing around the middle, and two solid sides to it that go out to a narrow tube. By squeezing those in and out like an accordion, the bellows is able to draw air in and then when we compress the bellows, we have now forced pressurized air out. That's the same premise that's happening in a pipe organ. It's drawing air in through a variety of different ways. The old ones, of course, worked very much like handheld bellows. Modern ones are able to draw air in through a different mechanical way. But either way, these bellows are providing pressurized air. Now, the pressurized air of a pipe organ is going to travel through a series of different pipes and different pathways. The organ has a few different mechanisms that are going to work as valves. So as we talked about in the last lesson, we have valves that either open or close a passageway, thereby either containing the pressurized air or by allowing it a pathway to leave. Now, in the case of a pipe organ, one of the things that exists is what we call the stops. The stops are a series of valves. If we pull the stops out in a pipe organ, we have opened the valve. Therefore, air can pass through the area that that stop is attached to. If the stop remains in, then of course that valve is plugged, and so the air won't pass through. Now, the stops affect how much air passes through over to the keyboard itself. And the keyboard works in a similar way as well. Each key, when pressed, opens up an air passageway that is going to make its way to the pipes of the pipe organ itself. Now, there's also pedals on the foot area of the organ that can do the similar thing. So between all three of these, the stops, the keyboard, and the pedals, we end up with a huge variety of different ways that air can pass through a series of channels and make its way out to the pipes of the organ itself. And so, working like a very complex recorder, all of this airflow is directed in different means so that it can get to the pipes themselves. Now, the pipes of a pipe organ are, of course, a bunch of long cylinders. And just as we know, they have different volume based on how long they are and what is their diameter. And so, just as we talked about with frequency, the bigger the pipe with the larger the diameter is going to have a lower frequency and therefore make a lower sound. A shorter or more narrow pipe will produce a higher frequency. And so, the pipes have a direct relationship to the sounds that they're going to produce. Now, the player of the pipe organ is therefore able to control through a series of calculations how they're going to produce different frequencies through the different pipes. This then leads to the idea that a pipe organ is actually in some ways like an early version of a computer. There's a certain amount of input which is coming in from the air. Through a different way of routing that input through a series of switches, or in this case, the stops, we're able to force the air through different pathways. And then, of course, the output at the end will be how the air traveled through the pathways that we have created by either turning on or off various switches, or by opening or closing various valves. So when we return, our next lesson will be about vacuum tubes in the earliest of computers and how air pressure, in fact, allows us right now to communicate online.